start my fourth module. Okay, so fourth module. That module is basically basically based on the designing of controllers for switching converters. Okay, so this is our fourth module. After that, another module is there, okay, regarding your magnetics, design of magnetics for switching converter. So, so in this module, basically we are giving more thrust. Okay, we are giving more thrust on basics of control design. Okay, so basically switching converter. If you see the switching converters dynamics, so you can understand that and that converter dynamics is totally based on the most of the portions. That means if you say check proper manner, so converter dynamics is directly proportional on the parameter selections of that converter, the duty ratios, okay, so and the switching frequency. So it having important roles to maintaining the converter dynamics. Okay, so another important features in my last module, you can see that modeling. Okay, so modeling normally converter modeling we did for our we did for the designing of the appropriate for the mathematical representations for the converter topologies. Okay, so you can go for you can see that different mathematical idea was there. Okay, so basically as per their mathematical ideas, so different modeling strategies also be there. Okay, so by using different modeling strategies, so we can introduce we can represent our nonlinear switching converter in very accurate mathematical dimensions or mathematical representation. Okay, so from that modeling you can define your converter. Okay, you can define or you can realize your converter in mathematical form. So why it is important? Basically that designing of that control. Okay, so you know that all of you know that practically you have to working or you have to dealing with that converter having closed loop operations. Okay, so in open loop, what is the problem of that open loop? That range of operation may be high. Okay, so you are giving some input, you are getting some output. Okay, so all the time you are giving the input, so all the time you are getting some output. So if you see that you can see that if it is follow the Ohm's law, that means it having some of the linear zone of operations. Okay, so some of the portions are there for the cutoff region, some of the portion is the saturation region. Means between that cutoff and saturation, between means the on time and off times. Okay, so not like on time and off time. So between the saturation and cutoff region, so you can see the slope. Okay, you can see the slope of that converter. Okay, so from the slope you can realize that what is the tangent. Okay, what is your gradient of the systems. Okay, that is it is normally known as that identifications. Okay, system identifications in the terminology of control system, it is called system identification. The system identification is important to find out the gradient. Okay, to find out that gradient of that system dynamics in open loop. If you get that gradient from open loop, then you can go for that control design. Okay, so any of the control design. So normally if you know that ZN method, Ziegler-Nichols method, so where you can understand, okay, where you can understand that when you are designing that PI or PID, or when you are going to be design PI and PID controller, so in Ziegler-Nichols method, so you have to find out you have to find out the converter slopes. Okay, so first, not like converter, any of the physical systems. Okay, so that which portion is your nonlinear portion, which is your linear portion, so you have to to draw the tangent on the linear conditions. Okay, then getting that value from the time constant, then you are going to be design the PI controller. You have to find out some of the expression. You have to take some of the expression. Then you are going to find out that control structures or parameters, different parameters of the controllers. Okay, so what are the parameters of the controller? Like you can say like that gain of the controller, pole location, zero locations. Okay, so that's the way you can represent the entire the system. Okay, that is our motivations. Okay, so you can understand the motivations of the modeling of the switching converter. It is your second stage. So if you see the curriculum, our course curriculum, first we have discussed about the introductions, then we are going to be discussed about the switching dynamics. Okay, or the, you can say like that, very brief idea about your solid state devices or the topology of the switching converters. Okay, so that is totally based on your converter topology chapters. Okay, what type of topologies you are using. Then we are going for the mathematical modeling. Okay, so if you fix up your converter topology as per your application, then you have to represent the converter as the form of mathematics. Okay, as the form of mathematical analysis. So you will find out that modeling, that mathematical analysis by using that converter modeling. After doing that mathematical modeling, you have to go for that controller designing. Okay, otherwise you are not able to design the closed loop operations of that, means accurate closed loop operation, that converter. So you can make it closed loop, but if it is not within the range, means if it is not within the zone of application, then it will not work properly. Okay, so you have to make it optimum response. You have to make it in as per your conventions. Okay, so you have to do it as per your requirement. Okay, so that's why we have to go for the appropriate selection of the controller. The motivation of this chapter is to design the controller, okay, for your respective switching converter. So if how to get that respective switching converter dynamics, so you have to know the converter dynamics. If you know the start mathematics, mathematical idea of the switching converter, from that you can go for the transfer function of the converter. That is preliminary or first prerequisite for designing of the controller in LTI domain. Okay, so especially our this course is designed for that LTI system. Okay, so we can go for other means other nonlinear control, other thing, but that course will be very huge, very vast. Okay, but we have to touch all the important portions in very moderate way. Okay, so you can go for other control ideas, other control structure, but in that case you have to go for that further studies, means then we are not able to accommodate the entire course within a single semester. Okay, so we have to cover everything within a single semester, within a single limitations of the time. Okay, that's why we are much more focused about that controller based on your LTI, means linear time invariant system controller. So okay, so if I get some time, additional time, then we can discuss some of the portions. Okay, for your advanced control strategies, if I get some time. So I don't think that for this semester where I am getting a lot of time. Okay, so basically we have to converge everything within 2-3 weeks. Okay, that's why we have to be quite hurry about it to conclude our syllabus. Okay, to complete our syllabus. Okay, as early as possible. Okay, so that's why we have to know the very basic idea of the control system, that all of you having completed your UG courses. So that means I can realize that you have already a good means good idea about the control system, very basic control system. Okay, so still I am giving one to some examples for to realize that which portion is important for our study, and we are realizing those basic study with our convention, with our switching converter studies. Means we can take one example of any of the switching converter. For this study we are taking that buck boost converter. Okay, for example. Okay, and we can do that same thing. Okay, that you have gone through, that you already gone through in your UG courses. Still I am giving some of the preliminary slides. Okay, today I am giving some of the introductory portions of that control ideas. Okay, that is related to your control design of your switching converters. Okay, that's why I am recap some of the small portion of that. Okay, so that is important for your curriculum. So here you can see, so I think all of you are able to understand the basic motivations of this chapter. Okay, so here you can see our main motivation is converter transfer function. So we have to find out the converter transfer function and its suitable controller. Okay, that is our basic motivation. So here you can see that's why we have to analyze the entire thing into two mode. One is called time domain analysis, another is called frequency domain analysis. So time domain analysis means you have to check the system, so you have to model the system in the form of transfer function. If you get it, so you can find out the you can go for the state response. For time domain analysis, normally we are doing it for the state response, okay, and find out the rise time, peak time, okay, so what is your peak percentage of peak overshoot, okay, then what is your steady state error, okay, so steady state time means state, okay, so that you need to be find out, okay, so that is for time domain response. For the frequency domain response, what you need to find out, so first thing is that in frequency domain you are going to find out that gain margin, okay, gain margin, phase margin. If gain margin is there, so phase crossover frequency, then phase margin is there, so gain crossover frequency, okay, what is this cutoff frequency, okay, so you have to, if you have the transfer function, now you have to represent in the for the stability issues, no, so you have to check the stability of the converter, okay, so how much variations of your parameter means parametric uncertainty, okay, parametric uncertainty means you have that converter parameters means in your previous chapter you can see which are the basic prerequisite for that converter dynamics means converter parameter like your input voltage, output voltage, capacitor value, inductor value, load resistance, okay, so you have all the parameter value. Now you are checking the parametric uncertainties means you can say like that your parameter you can vary plus minus 50%, okay, so you can check that value, okay, parameter that how much deviations in your output you can observe in closed loop, that is called that parametric that is called the parametric uncertainties. And what is your robustness study? So robustness study means your variation, so you have some disturbance, you are giving some of the disturbances to the system, okay, and you can say that you can tell like that how much robust your converter and the controller is it, okay, you have to calculate the robustness, okay, so how much robust your system is there, okay, with the presence of the disturbance, and how much percentage of error you are providing to the system, okay, so you are giving some of the reference in your system means that is your reference input. So if you give some of the disturbance means additional value of your reference means you know about the reference tracking, okay, and that reference tracking means you having some giving some of the reference voltage to your system or the reference current to your system. Now you are going to be add that some of the stepping value with your reference, okay, so that may responsible for the, if your converter is working good in closed loop, then your output always vary that reference value, okay, means you know that reference value means you can just realize that figure in my last class that you are giving some reference voltage, you are sensing the output voltage, then one differential amplifier was there, okay, so that reference voltage coming to the plus point of that differential amplifier, and your output voltage, that is the actual one that is sensed from the output terminal of your converter, that is coming to the negative portion of your differential amplifier. So reference tracking means that V reference, after that the differential amplifier provide you the error, okay, so that error is passing through the compensator circuit. So reference tracking means you are giving some additional voltage to with your VF, okay, so 50% of your reference voltage maybe like that, so positive 50%, negative 50%, maybe your output voltage is 12 volt and your reference voltage is 12 volt, so that select reference voltage select the output voltage of the converter of the closed loop condition, okay, so your output should come nearer to the 12 volt. Okay, that portion is not coming. If your output voltage is not coming up to the 12 volt, you can say like that there is some error. Okay, so now you are changing the reference value up to plus minus 50%. So plus 50% of 12 means it is 6 volt. Okay, so now at that instant you are adding 12 plus 6 volt. Okay, that means your reference voltage is right now 18 volt. Okay, you have to check that your converter is coming up to 18 volt or not. If it is directly tracking to the 18 volt, that means it is directly coming to the output of the converter is coming to the 18 volt. Okay, so you can say like that your converter is perfectly working. Okay, okay, so if again then minus 50% deviations means, so 12 minus 6 volt, that means suddenly you can change or suddenly you just reduce the reference voltage 12 volt to 6 volt, and you need to check what is your converter output. If it is coming exactly nearer to that 6 volt, so you can say like that your converter is perfectly working on your closed loop condition. So that is called robustness study. Okay, so how much robust how much robust is your system. Okay, so another two studies in there in robustness study, that is your additional voltage disturbance in your input side, means input voltage may be 5 volt, so you are giving additional 50% volt, means additional 50% of your input. So 5 plus 50% of 5 means 2.5, so input is 7.5. So as per your convention, if your converter is robust, so your output should be fixed as a 12 volt. So we are considering for the prerequisite, input is 5 volt of the converter, output is 12 volt. So how do you robust your converter? So your variations, input variation is 50%, okay, of your reference input value, means your input value you have designed for the converter is 5 volt. Now your input value is 5 plus 50% of 5 volt, means 2.5 additional, so 7.5, but your output is coming perfectly 12 volts. So you can say like that your converter is robust. Same thing for plus minus 50%. I am telling you that input side, actually plus minus 50% is not possible. So most of the cases you can say plus minus 10% of your input side variations. Okay, if you are designing your converter up to plus minus 50% means you can say like that your converter is very good. Okay, in output voltage also you can stay the same thing, that is plus minus 50% you can do it. So output is you can suddenly reduce that load resistance. Okay, load resistance, so that may cause for additional current to the system. That means your output side, so additional current means power should be constant, voltage will be down. Okay, so load variations you can do it. Okay, so to checking your output variations means output voltage regulation, so that is called input voltage regulation for disturbance in your input side, and disturbance of your output side, that is called output voltage regulations. And you are giving additional voltage, okay, additional plus minus voltage to the reference, so that is called tracking performance of the controller, of the converter. So these three are example for that robustness study of the converter. So practically it is happened. So how do mathematically represents? Okay, so depending upon of your disturbances, your converter is working well in closed loop, but you have to design the controller, appropriate controller. So how do you getting that controller? That's the basic motivations for this chapter. Okay, so you have to design the proper controller. Okay, that means that appropriate controller. So that's why we are recap in this initial portions of this chapter into few points, like we are going to be recap about some Bode plot. Okay, so first we checking that single pole response for Bode response. Okay, single zero response, if it is there single zero, then right half plane zero is there, so what will be that of the study? So frequency inversion is there, then combine both of them, then double pole response. Okay, low Q approximation, approximated root with degree polynomial. Okay, that is your basics study of the control. Okay, that means relevant to this chapter. So there are a lot of portion of your control system, but I am only picking these portions. Okay, basically it is relevant to our study. Okay, so we have to much more focused about the relevancy of the subjects. Okay, relevant topics of our subjects. So then we are going for that analysis of the converter transfer function. So after doing this portion, so we can go for converter transfer function study. So in this chapter, in this study, in this Okay, we are taking some example for a buck boost converter that I am telling you. So transfer function, the same basics for CCM converter, means continuous conduction mode converter. Okay, physical origins of the right of plane 0 of the converter. So these 3 points we are going to be discussed. Okay, so today our lecture is focused on these portions. Okay, this Bode plot and the basic idea about that structures. Okay, so today I am completed this portion. So in my next class I will discuss about the pending portion, means analysis of that transfer function. So in my present class I will discuss about this one. Okay, so design oriented analysis. So what are the most important point that I have already discussed with you, that how to approach the real and hence a complicated system. So for going to be the designs. Okay, so what are the most significant point we need to be studied. Okay, so that is your sometimes in my last I told you na, so state phase average modeling, if you convert are having 8 modes of operation, so there is a lot of mathematical complexity. Okay, so that problems also been discussed. Okay, what are the most important problem, that complicated derivations, long equation, algebraic mistakes. Okay, so due to complicated derivations and long equation, the algebraic mistakes will be there. Okay, so that points are important. Basically we are dealing with a lot of mathematics. No, there are a lot of complicated mathematics dealing with the matrices. Okay, so matrix calculations. Okay, so that is important issue. Okay, so you have to think about it and you have to practice more to grip all those mathematical ideas. Okay, so there should not be any algebraic mistakes. Okay, that you should be focused about it. Okay, that you should keep in your mind. Okay, then design of objectives. So what is the objectives? Design, why we are going for the design? So obtain the physical insight. Okay, physical insight leads the engineer to synthesize a good design. Okay, so we have to realize the physical insight. Okay, so practically the one system is working. Okay, so how accurately you are defined that system in the mathematical time. Okay, so that is the main motivation. So it is called the physical insight. Okay, then obtain simple equations. Okay, then obtain simple equation that can inverted, and so that the element value can be chosen and obtain the desired behavior. Equation that cannot be inverted are useless for the design. Okay, so what is the motivations for these inversions? Okay, so if your system, okay, you can say like that, you can take one system. Okay, so you are designing one system, so and get one transfer function. Okay, normal proper transfer function. Okay, so you are getting one proper transfer function, but if you see that transfer function of PID. Okay, so if you check it, so transfer function of the PID, is it a proper transfer function? No, it is not a proper transfer function. You can see that in PID controller, 2 zeros are there. Okay, 2 zero means 2 roots in your numerator. Okay, and 1 pole in your denominator. So what happened? Your transfer function is not proper. Okay, so you have to make it proper. So that's why we have to include 1 pole in your denominator. Okay, that is called that low pass pole. Okay, so low pass filter, that pole is normally developed for that low pass filter. Okay, so that you have to include additionally for stabilize your PID controller. Okay, so why that inversion is important? Okay, so if you see you have one converter having 2 pole 2 0. Okay, so in that case what happen, if you going for that inverting of that transfer function, okay, in there should not be any problem, so it should be the proper one. But some of the transfer functions, some of the converter transfer function like boost converter and buck boost converter, where you can see one 0 is there in right hand plane. Okay, so RHP 0 means right hand side 0. Okay, right hand plane 0 is there. Okay, so when it is working on RHP 0 with the transfer function, means your denominator having two roots, means converter having 2 pole, and your numerator having one positive side 0 and negative, another one negative side 0, means 2 roots are there, one is in your right hand plane, another one is your left hand plane. Normally left hand plane roots we are considering, we can say like that it is stable. Okay, so if you going to be reverse that transfer function of the boost converter, what happened? So if you going to be reverse, then your poles will be shifted to the zero, zeros will be shifted to the pole location. Then what happened? Your zero now, if you invert that, invert the transfer function of boost or buck boost converter, you can see that RHP 0, initially it was RHP 0, now it is coming, denominator means it is RHP pole, right half plane pole. So if any system having right half plane pole, so you can say like that, what? You can say like that system is unstable. Okay. So directly right half plane 0 means, right half plane pole means again it will be unstable. So you cannot able to invert the transfer function. But some of the control design like internal model controllers, okay, that is some of the example of advanced controller. So in that case, the prerequisite to design that IMC controller, internal model controller, in short form you can say like that, IMC internal model controller. The prerequisite of this controller IMC, okay, so you have to invert the transfer function. Okay, then you can go for the designing purpose. That is prerequisite to design that transfer function, to design the controller. Okay, so if you go invert that boost or buck boost converter transfer function, automatically it will be unstable. Basically, your right half plane 0, right now after inversion it will be right half plane pole. Okay, so that may cause for the unstable. That's why what you need to do in the special cases like boost and buck boost converter, you have to split the transfer function, okay, into two portions. One is inverting portion, another one is non-inverting portion. So your right half plane 0, that is coming to the non-inverting portion, and rest of the portion is there, okay, that is your inverting portions. Okay, I think you are all of you able to understand. Okay, so that's the features. Okay, so some of the limitations also be there, some of the prerequisites are there, that's the reason. So checking the inversion. Okay, so I think you are able to understand the motivation of this topic. Okay, so then final one, the design oriented analysis is a structured approach to analysis which attempt to avoid the problem. So structured based analysis should be there. Okay, basically some another converter like sliding mode control, okay, that controller are much more focused about to the structural analysis of your converter dynamics, then they are doing the calculations. Okay, so that's why sometimes it is important. Now another points are there, writing of the transfer function is a normalized form. Okay, so you have to find out the transfer function and you have to write it in normalized form, directly expose the salient features. So if you write in that manner, so you can understand the features, what are the salient features that I am telling you, that I am discussing right now. Okay, obtaining simple analytical expressions for asymptotes, corner frequency. So you have to much more focused about few points, that means your asymptotes, next one is your corner frequency and other salient features that allowed, okay, that you are other salient features means you can say like that, for your designing purpose, how much rise time you are wanted, settling time, phase margin, gain margin, that is another prerequisite. Okay, another salient features that you are specified. So for my specific converter, I want that amount of rise time, that amount of peak overshoot, that amount of phase margin. Okay, so if increasing of the rise margin, okay, so there is some direct relations of your time domain response and your frequency domain response. Okay, so the use of, here you can see that the use of inverted poles and zero, the use of inverted poles and zero to refer the transfer function gains to the most important asymptotes. Okay, the analytical approximations, of root of higher order polynomials. Okay, so important points, graphical constructions of Bode plot or the transfer function and the polynomials. Okay, so you can say like that your transfer function in the form of, you know, that ordered sequence equations will be there in the order of s to the power n. If it is second order, so s square, third order s cube, like that way. So we have to find out the roots from the transfer function like that way. So avoid algebraic mistakes. Okay, you have to avoid that one. Approximate the transfer functions. Obtain the insight into origin of the salient features. So you have to fix up the features. End of the day. Okay. So here you can see some your main motivation, desired behavior you have to obtain end of the day. Okay, that's why you are doing such studies. So first in this portion we are going to be recap some of the basic concept of the control systems. Okay, so so here you can see simple RC circuit. Okay, so simple points are there, so I can complete it very quickly. So simple RC circuit is there. So single pole response is there. Okay, from this, from what will be the transfer function? So for that R, it is, you can say like that, output by input. So output is your Vs, and you can say like that your input is V1. So you can calculate that thing. Okay, so it will be only R. So you will Laplace of this one. So it is the how much value is there. So current it is C dVc dt. So you are making it a Laplace transformation. So you can get that SC. Okay, that will be SC. dVdt means it will be a V2. Okay, that is coming directly, you can get that one. So V1, the expression of the V1, you can say like that by using KVL, you can go get it. KVL equal to IC into R. So SC dVc into the R. Another one is your only that voltage, it is your V2. So you can come, you can make a common that value. Okay, and what is your V1? So end of the day you will get that expressions. Okay, so you will get that expression. Is simple expression you have calculate from here. So what will be the rational function? So you can equate that one. So finally we will get 1 by 1 plus s plus rc, 1 by 1 plus src. Okay, so in the form of omega 0, okay, you can say like that 1 by omega 0 equal to rc. Okay, so your form of 1 by omega 0 equal to rc. So omega 0 equal to what? 1 by rc. So you are written like that, a normalized form. Okay, so now we have to find out that modulus value. Okay, so g omega, and now we are replace the all the thing, s is replaced by the j omega. Okay, g of j omega equal to what? G of j omega equal to 1 by 1 plus j omega by omega 0. So now you can make that j common over here. So it is coming 1 plus j into omega by omega 0. Okay, so that portion. So 1 by a plus 1 by 1 plus j plus j into omega by omega 0. So it is your s equal to j omega. Okay, so now we can calculate them. So cross value is there. Okay, so your elimination. So we are multiplying with that factors. Okay, both of the side. So finally what you are able to get, okay, what you are able to get, so you are multiplying, that means numerator denominator with 1 minus j by omega 0. So what happens? So it is coming 1 by, actually it is coming 1 minus, okay, within bracket j into omega by omega 0 whole square. So j square means minus 1. So it is coming 1 plus omega by omega 0 square. Okay, so 1 by j into omega by omega 0 whole divided by 1 plus omega by omega 0 whole square. Okay, so in magnitude form you are getting this one, that magnitude value. So that is your real value and imaginary value. You can separate them, and finally it is your value. Okay, so root under 1 by x square plus y square. Okay, that is your root under 1 by x square means 1 square plus y square means omega by omega 0 square. Okay, that you are able to find out. So what is your magnitude? So magnitude, you know the basic formula of Bode plot. So it is coming there minus 20 log that root under 1 plus omega by omega 0 square to the base 10. Okay, that dv is there. Okay, that is your imaginary portions and real portions. So it is your modulus value, that root under 1 by x square plus y square, that is coming modulus value, and it is your argument value, means amplitude value. So I think you know that one. Okay, so that is your polar form. So simple thing is there. Then asymptomatic behavior of the low frequency. Now you can consider for the low pass filter like that manner. Okay, so if your omega value is very less than, okay, omega is very less than your omega 0, and f is very less than of your f0. Okay, so you are considering that f0 point here. Okay, So you can say like that omega by omega 0 less than 1. Okay, basically omega less than omega 0 means omega by omega 0 less than 1, so it is coming that way. So then what is the modulus value? So you can get that value is very less than 1, so it is coming nearer to the 1. So g mod of g j omega equal to 1. So 1 mod means it is 0 dB per. Okay, it is 0 dB line. Okay, in a dB means it will be 0. Okay, basically log 1 means what? Log 1 means 1. That log 1 means 0, like that one. Okay, it is coming 0 dB. Okay, so you say like that, that value is coming 0 dB. Okay, so up to f0. After that you have to find out. So at the low frequency you are getting that as asymptote. Okay, that 0 dB per decade. Okay, so asymptotic behavior for the high frequency. For high frequency, so consideration will be reversed. So here you are written that omega less than 0, f less than f0. Okay, here you are written omega very less greater than omega 0, f greater than f0. Okay, it is your high frequency operation. So omega by omega 0 greater than 1. Okay, so now you can say like that it is 1, so it is coming compared to 1 means it is infinite, nearer to the infinite, and compared to the 1 means it will come in that omega by omega 0 square finally. So that value is coming root under omega by omega 0 square, so it is coming f by f0 inverse. Okay, so root means it is 2 will be square is there, it will be single, so minus. Okay, so up to this portion you will get that 0 dB per decay. Okay, then one inversion is there. Okay, if one inversion is there, so it will be minus 20 dB per decay due to the pole. Okay, you know that one. So that's why it is 20 dB per decay. So if it is minus 2, then it will be 20 dB per decay plus or minus 20 dB per decay. So twice. Okay, means it will be 40 dB per decay. But here it is 20 dB per decay. Okay, up to f0 it is coming 0 value. Okay, 0 dB. Okay, after that it is 20 dB per decay, minus 20 dB per decay. So high frequency asymptote mod of g j omega varies as f to the power minus 1 to hence n equal to minus 1, and straight line asymptote having minus 20 dB per decay is obtained. Okay, and value of 1 equal to f equal to f0. Okay, 1 means 0. Okay, value will be 1 means it will be 0 dB actually. Then nearer to the curve f equal to f0. So what happened at f equal to f0 exact magnitude, it will be 1 means root 2, 1 by root 2. Okay, 1 by root 2 means it is coming, if you see it is nearer to minus 3 dB. If you calculate that value, you are replacing that value 1 by it is root 2. Okay, so root 2 value is nearer to the minus 3 dB. Okay, at f equal to 0.5 f0. Okay, and 2f0, what will be the value? The similar argument will be similar. Okay, the exact curve is 1 dB below the asymptote, means exactly it is not perfectly 1 dB, it's below some value of the below, so that is minus 3 dB. That below is there, minus 3 dB deviation is there. Practically what happened? And 0.50 argument is same, but it is nearer to the 1 dB. Okay, same, it is also the 1 dB for 2f0 value, and it is minus 20 dB per decay line. So exactly it should come like that. Okay, that is your exact value. Okay, if you are doing exactly 0 means approximated. So here you are not considering that you are using that one, na? So you are using that equivalent. Okay, almost equivalent. Okay, exactly it is 1 by root 2, but you are making it 1. Okay, so it is sharp 0 like that way. But practically what happened, it having not 0 exactly 0, it having gradually decreasing that value, so it is 3 dB per decay. Okay, it is f equal to f0 at that point. Okay, I think you are able to understand that magnitude value. Okay, with the mod of g omega dB. Okay, then for the phase you have to calculate. So phase, that is 90 degree contribution, so both of the side. Okay, so it is pole means what, 90 degree contribution, so angular, that is y by x, so y is your what, omega by omega 0, x equal to 1, so minus tan inverse y by x. Okay, so that is coming like that one. Okay, so imaginary j omega by real j omega, angle of j omega tan inverse. Okay, so it is your imaginary portion, it is your real portions. Okay, so that angles is there. Okay, so it is your mod value. Then phase of j omega, so it is your zero asymptote. Okay, so angle is g omega. Okay, and you can see that 0, then it is coming minus 45 at f0. Okay, mid of the that 0 and 90, it is minus 90 for pole. You can see over here. Okay, angle g omega equal to minus tan inverse omega by omega 0, and now we are changing that value of omega, and you have to calculate omega equal to 0. So what is that angle? Omega equal to 0 means 0, tan inverse 0 means it is 0 degree. Okay, it is coming here 0 degree. Okay, then omega equal to minus 45 degree. Omega equal to minus 45. Okay, so for omega omega equal to omega. Okay, omega equal to omega 0 means tan inverse 1 means it is 45. So minus is there, so minus 45. So here it is minus 45 degree. Okay, then omega equal to infinite. Then infinite means tan infinite means 90 degree. So it's a 90 degree. So one pole is there, so angle will be minus 90 degree. Okay, so changing the value of f. Okay, the relation of f and omega is 2 pi f. Omega equal to 2 pi f. Okay, so that's why f0 means it is multiplication of some value. 0.01 f0 log values is there. No? You can see this is not normal deviations. This is logarithmic distribution is logarithmic distributions. Okay, so on the part you can see the logarithmic distribution. 0.1 f0, it is your f0, 10 f0, that 100 f0. Okay, so it is angle is there minus 15, minus 30, minus 45, minus 60, minus 75, minus 90. All our angles are there. Okay, so phase asymptotes are there. Okay, phase asymptotes for the low frequency equal to 0 degree, then high frequency it is minus 90 degree. Okay, low and high frequency asymptote do not insert. Okay, hence need the mid frequency asymptote. So all the things are there. Okay, so that I am telling you 2 pi f, the concept like that. So that's why it is coming f0 by 4.81. So approximated value is there. Okay, so try to meet frequency asymptote having slope identical to the actual slope of the corner frequency f0. So f0 is the corner frequency. So I think you know that all those things. So I'm just giving you the recap. Okay, so phase asymptotes like that way. So you are getting that phase asymptote 0. It is stating minus 45, and finally 90 degree. Okay, so it is your dotted line. So practically it is coming that way. Practically it is coming bending like that way, but it is sharp in ideal cases. Okay, it is coming to the sharp. Simpler choice. The same thing there. Okay, in the form of 0.1. So logarithmic scale is there. Okay, so summary of the Bode plot and the real poles. What will we look like that? Here you can see the Bode plots for 0 dB line, then minus 3 dB is decay. So practically at 0.1. Okay, so that value 0.5 f0. Okay, that is 1 dB decay. Again 2 f0, it is 1 dB decay. So finally it is 1 dB decay, calculated 3 dB decay for f0. Okay, so you are getting that transfer function, and what is your it is your gain. Okay, it is your gain, and it's your phase. Phase is coming starting from 0, then it is completed minus 90, and it is minus 45 at cutoff frequency, crossover frequency. So it is given f0 equal to what? f0 equal to corner frequency. You can say like that, corner frequency. At corner frequency it is coming minus 45 dB, and here corner frequency at decay is minus 3 dB per decay. Okay, then we can go for the single zero response. Okay, single zero response, what happened? It is the expressions in your pole that was in your denominator. Now it is your numerator. Okay, so magnitude expression will be like that. Okay, reversing of your pole. Okay, so in pole what happened? It was minus 20 dB per decay was there. Okay, for after the up to low frequency range, it will be 0 dB per decay. Means in high frequency range it is omega by omega greater than omega 0, so it is plus 20 per decay. So single zero means it is high pass filter, or single pole response means it is low pass filter response. Okay, so now you can give that. Now you are able to draw that angle. Okay, so what is your angular representation? So okay, it is your angular representation tan inverse omega by omega 0. with the exceptions of missing minus same as the same simple pole. So poles and zero pole are same, only the missing of minus. So same thing you can see. So it is coming from 0 dB line. Okay, so mod value means it is 0 dB line. Again at f0 it will be 3 dB per decay, changing is there. Okay, it is previously it was minus 3 dB per decay. Here you can see it is plus 3 dB per decay, and it is plus 20 dB per decay slope. It will rise up with the slope of that. So initially it was 0 degree. Okay, my angular points of angle means phase angle. Okay, phase is representation. It is 0 degree and finally goes to the plus 90 degree. At f0 it is coming 45 degree. Okay, so it's look like that. Okay. Right up plane 0 means you can say for the non-minimum phase system. So right up plane 0, you can see the normalized form is GS. It is 1 minus S by omega 0. So mod value, it will be look like your normal 0. It is 1 plus root under omega by omega 0. But in phase, it is look like your pole value. Okay, so it is the same, the real pole. Okay, I think all of you will able to understand. It is LPGA. So same as the conventional left half plane 0. Hence the magnitude of asymptotes are identical. Magnitudically there is no changes. Okay, it's look like the identical for the real 0. Okay, means single on 0. But in angle it will be behave like a pole. That's why it is called non-minimum phase. Okay, it will right half plane 0. So the LHP 0 exhibit the magnitude asymptote for the LHP 0. So okay, right half plane 0. Asymptote's magnitude is LHP 0 and phase asymptote is like a pole. So combination of it is magnitude will be like that for IHP 0. Okay, that Bode magnitude for the real 0. But phase margin it will be not like that. It will be pole like that. So coming from 0 then goes to minus 90 like that. You can check over here. That Bode plot and of RHP 0. Okay, so you can see that magnitudically look like a magnetically look like a 0. Okay, so it is coming 0 dB per decay, so it is plus 20 dB per decay. Okay, so here then here you can see plus 3 dB deviations are there. Okay, after that it is 20 dB per decay. But angular representation means polar representation, it is started from 0 like a real pole. Okay, and again the deviation is there at a minus 40 comes up to the minus 90. Okay, I think all of you are able to understand the simple thing. The frequency inversion, that is important thing. I told my importance of the frequency inversions. The reversal of the frequency of axis, the useful form when describing the mid or the half frequency of the flat asymptotes. Okay, normalized form of inverted pole is look like that. GS equal to 1 by 1 plus omega 0 s. Okay, it is 1 by 1 plus omega 0 s, and algebraic equivalent form is GS equal to S by omega 0. So we can multiply it with the S into omega 0. Okay, S by omega 0 multiplied numerator and denominator. So in numerator multiplied, so S by omega 0 with the multiplication of 1 in denominator. So it is omega 0 S by omega 0 and omega 0 by S into S by omega 0 means 1. Okay, it's look like that. Okay. The inverted pole format, emphasize the high frequency gain. Okay, so that may responsible for high frequency gain. Okay, so what will we look like that combinations? Okay, so one pole is there, one pole is there, one 0 is there. Okay, due to the 0, so it will be initially that due to the 0 you can see it will be starting from what? It is 0 means it is starting from 20 dB per decay. Okay, so it is starting from 20 dB per decay. Okay, so starting from here 20 dB per decay, 0 is there. Okay, so that's why 20 dB per decay for mod. Okay, then what happened? Then you can see one pole is there. So you have to check the frequency. If the 0 frequency is fast, okay, so you have to check that value of frequency. So which frequency is first? So first 0 frequency or pole frequency? If the 0 frequency is coming first, then what happens? First the Bode plot, the gain plot of this Bode diagram will follow first the trajectory of the 0 asymptotes for the 0. Okay, so here you can see the 0 frequency is first. So that's why initially it is follow the 0. Then what happened? Then if the pole is coming, so due to the pole that deviation will be like the minus 20 dB per decay. For 0 it is coming 20 dB per decay, plus 20 dB per decay. For the pole, it is coming minus 20 degree per decay. So now they are cancelling each other. For the 0 20 degree per decay, when pole is observed in your study, so it will cancelling means addition with the minus 20 degree per decay. So 20 degree plus 20 degree per decay for 0, addition minus 20 degree per decay for pole. So both are cancelling each other, so you will get the 0 value here. Okay, so the deviation is 3 dB per decay. Okay, so that is 1 dB. So that's why if the reverse thing is happened. Okay, so first it will be minus 20 per decay, means it will goes down. Okay, due to pole, then 0 is introduced, then it will be started. So for the 0, it will be started with 90 degree. Okay, then at f0 it will be what? It will be 45 degree. Okay, then what happened normally? Then minus 90 degree, and for the pole it is plus 90 degree, then it will be 0. Okay, for the single 0, it is started from where? For the single 0, you can see it is started from 0. Okay, then it goes up to plus 90. For single pole, it is started from 0, goes up to minus 90. For 0 pole, you can see over the started with 90 degree, then f0 it will be 45 degree, finally goes to the 0. So why 0? I think you are able to understand. Plus 90 for the 0 and minus 90 for the pole. So at that point, at that 10 f0, at that point, that plus 90 plus or minus 90, that's why it is 0 degree. And same thing is reflected to the gain plot. So plus it will be started with plus 20 dB per decay. Then at that point f0, that it is similar to your pole gain and your 0 gain. So it will be plus 20 dB per decay plus or minus 20 dB per decay. So that may cause for 0, it is 0 dB per decay. Okay. So inverted 0, here you can see the reverse thing happened. So initially what happened? Initially you are making it that 1 by 1 plus omega 0 s. Now the inverse 0 repeating was there. Only 1 by only you can see that 1 plus omega 0 by s. Okay, the normalized form of inverted 0. So first one, inverted pole. Okay, so it is your inverted pole. It is your inverted pole. Okay, so it is your inverted pole. First one. First one, it is your inverted pole. Now you are checking that inverted 0. Okay, for inverted pole, first 0 value is coming. Okay, for the 0, these two are maintaining as 0, then it will adding at that point. Adding is minus 20 per decay and it is coming 0. Okay, same thing at that point f0 plus 45 degree, then it is coming 0. Now we are going for inverted 0. The same thing is there. Okay, not same thing, that calculation will be like that way. So here you can see it is started with minus 20 dB per decay, that I am telling you now in my previous slide. And at that point f0, you can see minus 3 dB per decay, deviation is there. So at that point you are checking that minus 20 per decay. For the pole, it will be adding with the 0, that having plus 20 dB per decay. Okay, that's why it will be 0 dB. And for the pole, for angular plot, for the pole it is coming minus 90 degree, then f0 it is minus 45 degree. After that, at this point you are getting the 0 degree. Why it is 0 degree? For minus 90 for the pole plus 90 for the 0. So both are getting 0. Okay, that's the motivations of this, that's the working of this study. So here you can see that inverted 0. Okay, that omega 0 by s. Now you are making it multiplying with s by omega 0. So finally it is coming like that. Numerator and denominator. So both the cases you have to multiply. And for the nullifications, the other inverted 0 format emphasizes the high frequency gain. Okay, so it is a high frequency gain. So you can understand that gain plot and your amplitude plot, that is started with plus 20 per decay. So that asymptotes for the inverted 0, and at that point f0 you are making it 0 for addition of another plus 20 per decay. Okay, so same thing also happened for your polar plot. So in a frequency plot, it is starting from 90 degree per decay, 90 minus 90 degree, in minus 45 degree at f0, and it is at 10 f0, it is adding in plus 90, so directly it is coming 0. So this is your normalized form of your inverted, but it is inverted 0. Okay, so now we are combining them. Okay, so combinations, both of them. So suppose that we have construct the Bode diagram of two complex values. Okay, so now you are Bode diagram for two complex values. So we have to combine them. Okay, so for the combinations, you can see of two complex values functions of the frequency are there. So it is g1 omega plus g2 omega. Okay, it is desired to construct the Bode diagram of the product g3 omega equal to g1 omega into g2 omega. So combinations, like your individually there was a pole, individually there was a 0. Now what happened in this point, you are combining them. Okay, combining the poles and zeros. Okay, what happened, that you need to check it. Okay, so express the complex values of the function of the polar form. So it is coming g omega equal to r1, that r1 omega into e j omega j theta omega 1. Okay, so that g2 omega, r2 omega e j theta 2 omega. So g3 omega, it is h omega into e g theta 3 omega. So product of g3 can be written as that g3 omega equal to g1 omega into g2 omega. So r1 omega into g omega. So you are adding them. Okay, so finally you have to find out the combined gain. Okay, gain plot and phase plot. Okay, so it is your phase 1. Okay, composite phase, and it is your composite gain. Okay, from here you are getting the composite magnitude. Right now it is your r1 omega equal to r1 omega into r2 omega. So you can say like that in dv form, it will be logarithm now. So we are making in log both sides. So log of multiplication to component is adding of them. Okay, so logarithmic. So composite phase and sum individual phases. Okay, composite magnitude when expressed in dV, the sum individual magnitudes. Okay, I think till now you don't have any kinds of problem. I think it's a recap portion, so you are much more aware about it. So no problem is your side. Okay, then we can go for second order system. That was totally for the first order system. Okay, so I think there is no problem for me, sir. If you want any doubts, so you can ask me. So,
Hello, sir. Good morning, sir.
huh? Hello. Okay, so after that we can go for the next point, that is your quadratic pole response. So if you have any doubt, you can ask me, no problem. So I can go for that next slide. So here you can see the quadratic form or quadratic pole response. Okay, so it is my quadratic that circuit diagram. Okay, the basic diagram of two pole low pass filter example. Okay, so first we started with that low pass filter for the single order, then it is second order low pass filter. Okay, so LC circuit is there, one R is there, so you will find out that V2 and V1 is. So you know that basic example, so basic structure how it is coming, so I am not going to discuss it again. So now we represent that system in the quadratic form, 1 plus A1s plus A2s square. Okay, so what is the value, A1 equal to L by R and A2 equal to LC. Okay, so here the approach, you can see the approach. Okay, so just wait for a moment.
Sir, good morning, sir.
Good morning. Hello.
Hello, sir.
Okay, so in this approach one, so we have to see our denominator. Okay, so from the approach one, that factor of the denominators, what are the most important factors? So it is the quadratic form of equation. So now you have to find out the roots. Okay, so construct the Bode diagram and combine of the two real poles. Okay, quadratic formula. So you are getting that formula of a value of S1 and S2 from the form of Siddhartha. Just you know that expressions from the Siddhartha formula. Okay, so if that A4A2 greater equal to A1 square, that means 4A2 greater equal to A1 square, means A1 square minus 4A2 equals to less equals to 0. Then what happened? So the roots of S1 and S2, the roots S1 and S2 will be the real and can construct the Bode diagram at the combination of two real poles. Okay, if 4A2 greater than 4A1, okay, it is less than 4A1, okay. So if it is greater than, then roots will be complex because that root under value will be negative. Okay, so that assumption was made that omega 0 is real. Hence, the results of that section cannot be applied. We need to some additional points. Okay, that you have to calculate. Then you can see in approach to the define of a standard normalized form for the quadratic case. Okay, so you have that quadratic equation. Okay, so now you are represented in the form of quality factor. Here you are form of in the zeta value, and here you are represented in the form of quality factor. When the coefficient of S are real and positive, then the parameter sigma, okay, so not sorry, zeta, it is zeta, and omega 0 and q also be the real and positive. That all are the prerequisite. I think you know that very basic options for the control. Okay, you know that any of the concepts. So parameter zeta and omega 0, that q, so find as a equating the equation S, the parameter of omega 0 of the angular corner frequency. So we can define f0 equal to omega 0 by 2 pi. Okay, the parameter called the damping factor. Okay, so zeta is your damping factor. Okay, and control the shape of the exact curve of the vicinity of f equal to f0, the root of the complex when zeta less than 1. Okay, and q will be, if the q will be greater than 0.5, so at the vicinity f equal to f0, and quality factor q is called as a quality factor. Okay, these are the very basic prerequisite. Okay, any of the study, so it is more or less same. So what is the value of the q? Okay, so second order system, it is zeta and q are the related accordingly. So what is q factor? So definition of the q or quality, you can say like that, quality factor 2 by into peak energy stored and peak energy dissipated per cycle. Okay, so q is the measure of the dissipation of the system, and a is the more general definition of q for the sinusoidal exceptions of the passivity element of the system. Okay, the second order passive system for the two equation above are the equivalent. So we see the q of the simple interpretations in the Bode diagram and second order transfer functions. Okay, so we can understand. So the relation of q and zeta is q equal to 1 by 2 zeta. Okay, so that relation is there for the q factor. Okay, with the damping factor. Okay. So now we can represent in the form of q factor and damping factor and find out the value of q equal to r root under LC by L for two pole low pass filter example. Okay, so it is Vs equal to V2 by V2s into by V1s. Okay, so it's the transfer function from 1 plus S into L by R plus S square LC. Okay, equate the coefficient of the light power S of the standard form. So Gs equal to 1 by 1 plus S by q omega 0 plus S by omega 0 square. Okay, so it is f0, so you have to find out that f0. Okay, so expressions of the f0 and q. Okay, so in f0 previously it was the corner frequency. Now you can say like that. Then magnitude asymptotes, now you have to find out, you know that formula. So if now you are replacing that value with the j omega. Okay, so you have to find out the asymptotes for the replacing A is equal to j omega for the quadratic form. Initially we are doing it for single pole configuration for the first order system. Now we are doing the same thing for the second order system. For the second order system, you can see one important point, it is -2. Okay, initially for G equal to mod G value is nearer to the 1, so ln1 means 0. So initially it is coming nearer to the 0 dB per decade. Okay, up to f equal to 0 means corner frequency. Now what happened after that? You can see it is f by f0 to the power minus 2. Initially for the first order system it was minus 1. For the second order system it is coming minus 2. So due to the minus 2 means it is 2 into minus 20 dB per decade. Basically it is pole, so due to the pole it is coming minus 20 dB per decade. Okay, that's why it is coming minus 20 dB per decade, and f by f0 to the power minus 2. Okay, it is coming like that. Okay, so it is a frequency response. Okay, and mod G of j omega dB. So the deviations, okay, the deviations of exact curve from the magnitude asymptotes. Okay, so I think you are getting this one, no? So square of the real part and the imaginary part. So that j omega you can place over here. So it is coming j omega by q omega 0. So the j means it is imaginary part. So if you are giving the modulus form, mod form, so it is coming j by omega 0 square. So j square by omega square, j square omega square whole divided by omega 0 square. So j square means minus 1. So it is coming 1 minus omega by omega 0 whole square. That's why it is coming. It is real part and it was imaginary part. Only j by omega 0. So that's why 1 by q square into j by j. So I think you are all of you able to understand, na? So there should not be any confusion. Okay, so if you have any problem you can ask me again. I can repeat some of them. Basically this is very basic form, that's why I am moving very quickly. Okay, so here you can see for the f0 you have to calculate, but practically at the f0, so if it is omega equal to omega 0, you can put that value omega equal to omega 0, then it is coming 1, so that portion will be 0. Okay, so omega equal to omega 0, it is 1, so it is coming 1 by q square. Okay, root under 1 by q square. So finally it is coming mod g j omega equal to coming the value of mod value of q. Okay, so how much value of q? If it is less value means nearer to the 1, so it will be 0. Okay, so it should not be practically it is not 0. Okay, practically it depends upon mod value of q. So low q value means nearer to the 0. High q value means it is extreme value. Okay, so high q means what? You can get the expressions. So low q value means if the value is less than 1, so peak store energy is less than of your energy dissipated, means energy storing is less compared to your energy dissipation. Okay, compared to your energy dissipations. Okay, it means like that. Okay, so if it is greater than q value is greater than 1 means peak store energy greater than of your energy dissipation. So energy dissipation is less. Okay, so high q value means you can see like that in my next picture. You can see high q value means it is coming upper. Okay, so it is coming up to 0 degree. So dB value is, if high q means q equal to infinite means this one. Then gradually decrease means up to coming at 0.7, 0.1. So 0.1 means nearer to the 0. Okay, that is 1 means 0 nearer. So nearer to the 0, 0.7 means less, and 0.q1 means very less. And you can see the phase margin, same thing, same way. Okay, so it is your mod g value, practically it should be 0 dB. Okay, so it is having some mod value. So the exact curve of the magnitude q at f equal to f0, the deviation of the exact curve from the asymptotes, it is coming that mod q dB. Okay, it is mod q dB, and that value is minus 40 dB per decade. Okay, so it is your q value. I think all of you are able to understand. Now less value of q, now we are doing that plot in f by f0, that value of q. So value of q is coming less means it is your base value 0 dB, so 0 dB value. So less value means it is minus 40 degree. All the cases it is coming minus 40 degree. Okay, minus 40 degree, but it is coming less. Okay, so phase margin, if you plot that phase. Okay, so phase plot you are checking, so you can see that one. Okay, so phase plot is there. So similarly, so in if you check the phase plot, so there is no pole. Okay, sorry, there is no 0. All the poles are in your x-axis. So phase plot will be what? It will be coming starting from this figure, you can see that maximum will be minus 180 degree. Okay, so that's why it is coming like that phase plot. So 0, starting from 0, and it is completed up to minus 180 degree. Okay, so starting from 0, so it is like that starting q equal to infinite, q equal to 10, 5, like that way. Okay, so that value is near us. So if it is 180 degrees, so if that value is like that, so like that way. Starting from 0 and completed point up to 180. It is your angular, means polar plot, and it is your magnitude plot. Okay. So now the low Q approximations. Okay, if the value of Q is low. So for a given second order denominator, the polynomial, the form. So you know the basic form of the polynomial. Okay, you can represent in this manner also, no problem. But in real loop, when the Q is value is less than 0.5. So if the value is less than 0.5, means below the 0 dB line, you can see that value is less than 0 dB line. That one. Okay, that is 0.5. Here you can see that Q value is 0.5 here. Okay, moderately. So normally we are selecting that Q value is 0.6. Okay, so for the critically damped system. So all the time our idea should be like that critically damped system. Okay, so for the critically damped system, we are normally designing all the system in the form for getting the critically damped system. Okay, so in Bode plot, the critically damped system is coming that phase margin for the 60 degree. Okay, especially for the second order system, and Q value is nearer to the 0.5 to 60, 0.6. Okay, like that way. So we can find that when the Q less than 0.5, so we can factor the denominator, the construct the Bode diagram using the asymptotes for the real poles. Okay, for the real poles, so we would use the following normalized form: GS equals to 1 by 1 plus s omega n, s 1 by 1 plus 1 by 1 plus s by omega 1 and 1 plus s by omega 2, that we are getting. So practically the desirable approach when Q very less than is 0.5, then when the corner frequency omega and omega 2 are well separated. So in this case, second order system, two corner frequencies are there, omega 1 and omega 2. Okay, so in your first order system, that one corner frequency is there, it is very easy. Okay. So for the example, for the RLC circuit, okay, for the RLC circuit, that the quadratic formula using the corner frequencies. Okay, to corner frequency you need to calculate the GS equal to V1 by V1S by V2S by V2S by V1S. Okay, so it is a transfer function. It is time 1 plus S into L by R plus S square into LC. The quadratic formula of the factor denominator corner frequencies are like that, omega 1, so that the Siddharth-Charj's formulas is there. Okay, simple thing, it is your V1, it is your V2, and L is there. Okay, and C, LC is there, and load resistance R is there. You are fetching the output voltage or getting the output voltage across your R. Okay, so factor denominators. Okay, factors of denominators omega 1, omega 2. So that what is written like that. The complicated expressions yield a little insight into the how the corner frequency omega and omega 2 depends on RLC. Okay, when the corner frequency are well separated in value, it can be shown that they are given the much simpler or the approximated expressions. Okay, omega 1 equal to R by L, omega 2 equal to 1 by RC. Okay, when omega 1 is the independent of C and omega 2 is independent of the L. Okay, this simpler expression can be derived via low Q approximations. Okay, I think you are able to understand the concepts. So value of omega 1 more or less same to the L by R, and value of omega 2 is more or less similar to the LC, 1 by RC. Okay. Then derivation of low Q approximations. Okay, given that GS equals to 1 by 1 plus S by Q omega 0 plus S by omega 0 whole square. The use of quadratic formula to express the corner frequency omega 1 and omega 2 in the terms of Q and omega 0 as omega 1 equal to omega 0 by q. So 1 minus root under 1 minus 4 q square whole by 2. So like two roots are there, okay, from the Siddharth-Judge's formula. So now we can go for that, calculate that corner frequency omega 2 and the corner frequency of omega 1. So first corner frequency of omega 2, so you have that expressions from that previous one, so it is your corner frequency of omega 2, that second expression. So okay, now you are varying that value, so which value you are changing, that fq depends upon your fq. Okay, so now q value you are changing 0.0, when it is 0, so it is coming 2 by 2 means 1, so it is started from 1, okay, when q equal to 0. Okay, that's why it is written fq, function of q. So you are having the value of q and your plot in your y-axis, it's a omega 2. Okay, so it is a function of q, that's why fq is written. Okay, so omega 0 by q. Okay, first you are making that omega q equal to 0. Okay, q equal to 0, so more or less it is coming to the 1. Okay, so then you can see that omega 2 equal to omega 0 by q into fq. So what is the value of fq? Fq equal to half into that, from here we can written in the form fq equal to half into half whole into 1 plus root under 1 minus 4q square. So if the q equal to 1, that first one, okay, tends q equal to 0. Okay, q equal to 0 means it is 1 plus 2, it is fq equal to 1. Okay, then you are making that q equals to 1, so it is minus 4, it is complex value will come. Okay, so minus 3 root under minus 3. Okay, so that case you are getting that complex value, so you have to, you are not change up to 1, but you should not go up to 1. So 0.5 first you are checking with the 0.5 q equal to, so it is 0, it is 1, so it is coming up to 0.5. Okay, at 0.5 it is coming 0.5. Okay, that q value equal to 0.5, sorry, the q value equal to 0.5, you are getting the value of fq equal to 0.5. Okay, below that 0.5 it is complicated value, means complex value is come. So 0.5 is a critical value. Okay, so it can vary up to 0.5 to 1. Okay, so for q equal to less than 0.3, the approximated fq equal to 1 and within the 10% of the exact value. So why the selection of q is, we are making it 0.5, so that is important thing. So below that 0.5, what happened, that is complex value. Okay, that is complex value. So that's why in normal cases we are making it that omega, that value is 0.5. The same thing in that same case for the crossover frequency, corner frequency omega 1. So you are getting the expressions of the omega 1 from Siddharth-Judge's formula, that is your expression of omega 1. Okay, so omega 1, so you are able to retain that functions of omega 1. So fq value can be calculate in this manner. Okay, for small q, fq tends to 1, then we are obtain that omega 1 equals to q omega 0 for that q very less than 1 by 2. For q equal to less than 0.3, approximated q equal to 1 is within the 10% of the exact value. So we are making that value. So same thing at 0.5, you are making the same thing for 0.5 up to 1. Okay, so that you are calculating over here with the variations of the q in the range of 0 to 0.5. Okay, q value is changed to up to 0.5. Beyond 0.5 we are not getting or not giving. Okay, that's why you are plotting over up to that point. So low q approximation. So okay, so low q approximations means for gain plot you are getting at 0 dB, so after that it is minus 40 dB per decay. So how much your omega 1 and omega 2, okay, that 2 points, how much that decay is there, that means omega 1 means f1 and f2 frequency and angular frequency, so that point, so it is getting that minus 20 dB per decay. Okay, so the changing that point for f0 for practical for the single order system. Okay, so it was directly coming as a that portion for the quadratic equation, so exactly minus 20 dB per decay line is there. Okay, so for the RLC example you are able to get that one. Previous example you are getting the expressions of V1s, V2s by V1s, and you are able to calculate the value of F0 and the expression of Q. But the low Q approximation leads for that value of omega 1 equals to q omega 0, omega 2 equal to omega 0 by q. Both of the difference you can understand, that value is coming, that approximate value of omega 1 is coming r by l, okay, and approximate value of omega 2 equal to 1 by rc. That was written over here first here. Okay, so here you are going to prove. Okay, at that condition you are make it proof. So here you are making it proof that value. Okay, I think till now you don't have any confusion. If you have any confusion, so please tell me, so I can rediscuss that portion. So in my next class I will discuss about the analysis of converter transfer function. That portion I will start in my next class. Okay, means Monday. Okay, I am taking one example for the buck boost converter and doing the same thing, and we are going to be studied for that. All the calculations, all the necessary steps, means dynamic studies. Okay, control dynamic studies. Okay, that is our main motivations. Okay, that we need to do. So if you have any confusions or any doubts, you can ask me, so I can rediscuss that part. Okay, otherwise I can end my sessions. Okay. If you have any doubt, you can ask me. Okay, so I think no queries or no queries from your sides. Okay, so if you have any queries, you can note it down to your notebook. So when I will start my next session, so means next day sessions, at that time we can rediscuss some of the portions, any pending portions, any doubts, any things are there, so I can discuss it. Okay, so thank you for my today's session.